Hello and welcome to A Space Math. We are going to make some beautiful Lissajous paintings. These are all the supplies we need. We're going to start off by cutting the bottom off of the ketchup bottle. We're going to poke holes into it and attach our safety pins. Now we're going to find a place to fasten our twine. This could be anywhere around the house. You can even use a couple of chairs. You just want to be able to elevate it. We're going to tie our twine to those safety clips. Make sure to tie it nice and tightly. We're going to make a slip knot at the top of that twine so that we can adjust the length. That'll be important later. And finally, attach the paperclip to the twine we attach to our fixed points. You should have a setup that looks like this. We're going to fill our ketchup bottle with some sand, raise it up at an angle, and simply let it swing. And you'll see that we create these beautiful, intricate patterns that we're later going to turn into paintings. Look at that. And we can see that if we make a few adjustments on our setup, we can make these beautiful different patterns. And the questions we'll be answering in this project are: what causes the different patterns of the curves? And can we use mathematical functions to create a visual art piece or painting with a specific design that we choose? We'll start our project by collecting data and using that to create a model. We're going to tie a string to an anchor point. This can be anything. Tie a paperclip at the end using a slip knot so that we can change the length. Finally, connecting a mass to the paperclip. Harmonic motion, moving back and forth around some central point, as we see here. Our amplitude is the maximum displacement, the furthest from the center that the mass gets. Our period is the time to complete one full swing, as you see here. Now, if we trace the motion of this mass, we see something familiar. Our amplitude here is the highest point of this dotted line, and our period is the time between the peaks. Pause and think, what family does this function belong to? It is a sine function. A stands for amplitude. The Greek letter omega stands for angular frequency. And omega is defined as 2 pi over the period. This is called a periodic function because the y values repeat themselves at regular intervals. But the question we have to ask now is, what determines the period? Does changing where we release it, the amplitude, affect the period? Does changing the length of the pendulum affect the period? And does changing the mass affect the period? Let's find out. Here we are going to test how changing the amplitude affects the period. How do you think changing the amplitude will affect the period? We're going to try different amplitudes measured from the center and record the time it takes to complete a full swing, and find the average period. And we'll repeat this process by changing the amplitude by equal amount for every trial and taking the average period until we have a data table as seen here. Now we're going to try a similar approach with the mass. How do you think changing the mass will affect the period? And here we are going to add mass for every trial and take the average period after we change the mass. I'm using fishing weights, but you can use anything that you have an accurate measure of the mass for. And again, we are going to change the mass by the same amount every time and take the average period every time until we have a full data table as seen here. Lastly, we're going to check for the relationship between length and period. How do you think changing the length will affect the period? We are going to use the same approach, changing the length by the same amount for every trial and taking the average period for every trial. Until we have a data table again as seen here. And here we see the data tables that I compiled in my trials. Notice here that the variable that had the greatest effect on the period is clearly the length. And now we're going to use technology to find a mathematical regression model for period versus length. And the important thing to know here is that the closer r squared is to 1, the better the model. We'll try the linear model, the exponential model. We're going to skip the polynomial model, more on that later in the extension video. The logarithmic model we are trying. We see clearly that the power series is the closest to 1. Now we see the equation that fits the data the best, and that is the model that we will use. Now let's quickly compare the model that we got from the data with the theoretical period equation relating period and length. A quick disclaimer here, this theoretical equation is meant for small oscillations. We're going to use it for simplicity's sake, but we'll talk more about why in the extension video. So we're going to simplify this equation by combining the constants and leaving L as the only variable. And the constants all together give me 2.006, and we still have the square root of L at the end. Comparing the constants of the two equations, we see that they are actually very close. And we'll allow ourselves to round the exponent of 0.49 to a half, which is a square root. And this will make it easier for us to work with this equation. Here we have our sine function, our definition of angular frequency, now we're going to use the model we found for the period of a pendulum to modify the sine function for our specific physical system. Now here we have the model of movement for our specific pendulum. Keep in mind that yours is probably going to be a little bit different based on your data. In our next milestone, we will design the curve that we will paint. Returning to our original setup, we see that we really have two sine functions that are at 90-degree angles from each other. One moves in the y direction, and and one moves in the X direction. Combined, these two functions create these beautiful parametric curves called Lissajous curves. But what exactly determines the shape of the curve? Here we have our parametric equation with the two sine functions making up the x and the y coordinates of the equation. As we change the parameter t, we see that we get different coordinates. Each value of t gives us a different x and y coordinate based on the values of the two sine functions. And as we plot more and more points, we see that we start to get the idea of what shape it's creating. Now let's explore how changing the frequencies of the two functions affects the shape of the curve. And again, we see that every value of t gives us a different x and y coordinate. And again, as we plot more and more and more points, we see the shape of this curve taking form. And here we have this cool little hourglass shape. And now, let's see how changing the amplitude of one of the functions will affect the shape of the curve. We're going to plot more and more points, and we see that we get a very similar shape, but with a different width. Now I encourage you to play with this to see how changing the two frequencies changes the shape of the curve, and find a pattern that you would like to recreate with your painting. In our last milestone, we will recreate our digital design with the pendulum system. These are questions to consider while you're recreating your design. I'm gonna try to create the 3:2 angular frequency ratio design, but first I have to figure out what the lengths of my strings are going to be. I'll use the angular frequency from my model to substitute into the two angular frequencies. Note that the two are different because they two have different values of L. If I solve this equation for one of the values of L, I know exactly how it's related to the other value of L. So here, my L1 has to be 4/9 the size of L2. I measured out at L2 to be 1.05 meters, which means my L1 has to be about 0.47 meters. Time to put our calculations to the test and try to recreate this design. It does create something really beautiful, but it's not quite the same as the digital design, so why not? So here you can go ahead and create the painting given the pendulum you have now. If you're curious as to why it's not exactly the same, check out the extension video where we explore these concepts and questions. Given the design and given the pendulum that created with my data and calculations, this is the painting that is created by that system. Our very own mathematical masterpiece. Please tag us on social media and show us your paintings, and subscribe and follow us to see what we have coming next.